Now I want to talk about this important article from KTH, a Bayesian attractor network with incremental learning. So I want to explain this important article in 2002. And there are also other important articles like this one, again by Anders Lansner. So palimpsest memory, standard correlation-based learning rules for attractor artificial neural networks suffer from catastrophic forgetting that I've explained it in my channel, in my playlist for continual learning. Another mostly forgetting learning scheme is learning within bounds, and where the connection weights are bounded. The learning rule for training pattern is just like this. But these weights are bounded. And C is the clipping function. I will show you at the end of this lecture how it is related to our talk. So what is the motivation of this paper? We demonstrate that by estimating the probabilities underlying network biases and weights by moving averages instead of counters as in the previous versions, it is possible to derive a continuous real-time Bayesian learning rule with the properties of palimpsest memory. The forgetfulness of the network can conveniently be regulated by the time constant of the moving averages. We evaluate this learning rule in the context of long-term and short-term memory properties of an attractor network with some biologically plausible elements. So this is the naive approach for classification. You know that you write the probability of your... So assume that we go from, that our cortex has 6 layers, but each one has some hypercolumns. But inside each hypercolumn, there are a lot of mini columns, and each mini columns, you select one, because, for example, each one is a different attribute. So it's a very sparse set of neurons that are active. And if you just write the equation for the probability of target, because assume that here is just the presynaptic area and here is the postsynaptic area, and each corresponding to its own mini columns, and you want to see which of these neurons will pick which one. And so the probability of your y and your x could be written as this. But if you simplify this, you will notice that this can be represented like this, and you consider O is just an indicator variable. But what is interesting is that you can write that weight that you always talk about in machine learning as this meaningful representation. So as I said, our neocortex has 6 layers, 1, 2, 3, 6. And you know that we have hypercolumns like this, but inside each of them there are mini columns as well. And so this is layer 6, layer 5, layer 4, but there is interaction between them. And also it has interactions with different different areas of the brain. So these are the columns that I said. There are mini columns inside the hypercolumns, and the layers from 1 to 6. And so this is the columnar organization of somatory cortex. For example, if you just touch something, you will see that some of them are active. But for example, this column corresponds to second finger, this column corresponds to third finger. So if these neurons are active, your brain understands that which of the fingers are touching. The same thing for visual thing, the same thing for different thing. But now here is a basal ganglia. It's also important. I mean, that those striatum corresponds to, everybody knows about decision making. It's like reinforcement learning and reward and those things. So the cerebral cortex just decides on the body movement, but this is the basal ganglia that executes actually your movements. The same thing for your eyes. There are some neurons inside your cortex. For example, they have discovered that it's in your fourth layer of your cortex, and this corresponds to some, for example, right eye, right, left. This is how it is encoded, and these are mini columns inside microcolumns, inside hypercolumns. There are other cortical areas, and they are related. For example, if you go to thalamus nucleus and also higher order thalamic nucleus, and also it has relation to hippocampus. So although each one, you can consider each one as a microservice, but they are related to each other. This microservice is related to another one, and that's why. And each one has as separation of concerns principle, only focuses on a specific task. And if you consider discrete valued attribute networks, the relations become this. Because now it's not just 0 and 1, but it selects which of these attributes it is talking. For example, if the J is selecting the J's one, J prime, then it could select, for example, number 8. It could select anything. So it's a multi-valued approach. The same formulation like we did before, like this, but now if we can generalize it to discrete valued attribute network, and you can write these equations. For simplicity, we call this term edge, because we will create a recurrent network from this edge. This is that nonlinearity that you see in any recurrent neural network such as ByGRU or ByLSTM, but it's very simplified, and a very simplified version of that. And here just a softmax of that. So this RNN that I'm talking about can be seen as a recurrent, so it's a recurrent neural network. But this is the edge that, for example, when it converges, you understand that, for example, the edge JT plus 1 from this, the iteration creates the next step. But if you just in the continuous limit, in the continuous case, you will see, and by the way, this tau c is very important, is membrane time constant of each unit, because each unit is different. But the time constant of them are assumed the same. And so we can also represent it as incremental Bayesian learning. So these were the equations that you saw in the previous lecture that I promised you that I explained this lecture. Now you understand the relation between them. But you may say that we don't know beta, so that's why we approximated using this exponentially smooth running average. You see, it's like exponential moving average that you see in trading Forex, or you see it in financial systems or financial markets. We do the same thing here. And here the equation for H. That is what is important. And to avoid logarithm of 0, the basic low activity is introduced. And now I want to talk about the weights. So the weights were set based on a sparse Hopfield network. And C here is the same clipping function, and rho is the average activity level, and the update rule was this. This guarantee a single active unit in each hypercolumn.